Okay, so today we need to cover the 3.5 and the 4.1. So the 3.5 deals with the 5-number summary, which are basically the information you need for the box and whisker plot. So um, the 5 numbers you need are the minimum value, quartile 1, the median, and the median is the same as quartile 2, quartile 3, and the maximum. So to come up with this data, you'll either use your calculator or StatCrunch, and I'll show again in a minute how to do that. So this one says every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the U.S. The following data are the interest rates charged by 10 credit card issuers randomly selected from July 2005 from the July 2005 survey. Determine the 5-number summary of the data. Okay, so then they give us the um, banks or the credit card companies and the interest rate they're charging. So if you're going to use a calculator to do it, you would hit Stat and then number 1 for edit. And then I already have the data in, but if you had numbers in that you didn't need, a quick way to delete all of the numbers in whatever column is to highlight the column, hit clear, and then enter, and it wipes out the numbers. So anyways, all I did is I typed these percentages into my list 1, and then I would hit Stat, arrow over to calculate, and then one variable stats, number 1. And then my information is coming from list 1. And then the stuff that I need for the 5-number summary is clear at the bottom. So I just scroll down, and then I have the information. So here's my minimum, quartile 1, my median, which is quartile 2, quartile 3, and my maximum. So now the way you would do that in StatCrunch, and I just opened up a problem from your assignment that asks for that 5-number summary. So when you're in your assignment and it asks for you to come up with that information, I just click on this little box in the top, open in StatCrunch. And then once it's open in StatCrunch, I hit Stat, Summary Stat, Columns, and then it was in variable 1. And then I can make sure I have I scroll down and I can see there's my minimum, my maximum, my quartile 1, quartile 3, and then sometimes you might need the interquartile range. Later on today we'll need interquartile range, IQR, so I'm just going to head and select that. And then I hit compute, and then I have my data right here. So then we can see that the data that I just barely came up with from StatCrunch is the same here. Okay, now it does say to use ascending order, so you're putting your minimum, quartile 1, quartile 2, or the median, quartile 3, and then the maximum. Now you'll also be asked problems about the fences, the lower fence and the upper fence. So this helps you determine if a data value is an outlier, if it's outside of the fences. So once you have your 5-number summary, your quartiles, then to determine your lower fence, all you do is you take your quartile 1, which in this case was 12, and you subtract off 1.5 times the interquartile range. So on this one, I don't have the interquartile range listed on the calculator. So to get the interquartile range, you take quartile 3 and minus quartile 1. But in StatCrunch, you can select interquartile range and just get that number. So my quartile 3 was 14.4, and then I minus off quartile 1, which was 12, and I get 2.4. So then to determine my lower fence, I take quartile 1, which was 12, and I minus off 1.5 times my interquartile range, which was 2.4. And then to get my upper fence, I take quartile 3, which was 14.4, and then I add 1.5 times my interquartile range. Okay, and I did these earlier, so I already have it in the calculator. So my lower fence was 8.1 and my upper fence was 18. Now the way a box and whisker plot is drawn is you take your values right here and you have to find a scale that you like. So 6.5, so I'd go like lower than 6.5, like maybe 6 or 5. My maximum's up at 14.5, so maybe 15. So you pick some sort of um, interval in which you can get from the minimum to the maximum. So I'm going to choose to start by 5. And then I could add by 2s, I could add by 1s, it's up to you. I'm just going to add by 1s. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So then the box and whisker plot, my minimum, that was at 6.5. I would put a point for that. My quartile 1, which was at 12. My median, which is 13.6, which would be about right here-ish. My quartile 3, which is 14.4. And then my maximum, which is 14.5. So those are really close together. And then the middle 3 dots are what forms your box. And then the median, you do a line through it. And then you draw your whiskers. Okay, now my upper fence was 18. So if I had anything over here, that would end up being an outlier. My lower fence was 8.1, which is about right here. So that meant that this value over here, that minimum of 6.5, that's an outlier. So what we usually do is instead of drawing a whisker to that outlier, they usually will just do that as an asterisk and then not draw this line right there. Okay, so this shows how it would be. So since that was an outlier, they just went with the next smallest. So after the 6.5, the next smallest was 9.9. And so they used the 9.9, the next smallest value, and drew to that one in the outlier over here. So this just lets you see the relationship between the box and whisker plots and histograms. So when we talked about skewedness, this first one right here is right skewed. If I were to try to draw a, oops, that was not a very good approximation of that. If I were to draw a curve on this one, we can see that this tail to the left, it's longer than anything over here. So this is right skewed. With the box and whisker plot, you can see that the whisker is longer on the right, so that lets me know that it was right skewed. And then when you look at the median or quartile 2 is closer to this other end of the box. So when it's right skewed, you have a longer tail on one side, and then the median is closer to the short tail. When you have nice symmetrical data, then notice my whiskers on either side are about the same and the median lands pretty much like right in the middle. And then this one that's left skewed, you can see that the whisker is longer to the left and the right is shorter, and the median is closer to the shorter tail. Okay, I think that was everything that we dealt with in the 3-5. So now we also need to do the 4-1. So 4.1 deals with scatter diagrams and correlation. So we have a whole bunch of vocab here. So it says the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory value is plotted on the horizontal axis, and that's the x-axis, and the response variable is plotted on the vertical axis, which is the y value. Now, just because, like here they're doing depth and time, just because you graph something along the x-axis and graph it with something on the y, doesn't mean that the data is related. Okay, so it is possible to graph anything you want, but it doesn't mean that there's a relationship necessarily between these things. So this one says drawing and interpreting the scatter diagram. The data shown at the right are based on the study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which the drilling begins is the explanatory value, or the x, and the time in minutes it takes you to drill 5 feet is the response. Okay, so from here we can see, like when you start drilling at a depth of 50, it took them, it doesn't tell us if this is in minutes. I'm just going to pretend that's minutes, time in minutes. So if you started at a depth of 50, it took a little more than 6 minutes to drill 5 feet. When they started at a depth of close to 100, it took a little bit over, maybe like 7 feet or something. No, 7 would be up here, so a little bit, so 6 point something. Somewhere between 50 and 100, it took like closer to 7 minutes. But you can see overall, if you could draw like this little linear line, the data seems to be going around that linear line. So this is what we would call a linear relationship. Now, we also have something called the correlation coefficient. So even though I could draw a linear line, we need to determine if this linear line, how well it fits the data, and that correlation coefficient will help us with that. Okay, so this lets us see the various types of scatter diagrams you could have. If the data seems to be going upward from left to right, then that's linear, a linear positive relationship. If it goes downward from left to right, this one seems to be going down, then it would be a negative linear. It doesn't have to be linear. We usually deal with linear, but this one shows that it kind of looks like quadratic. This one looks like it could be like a cubic. And then that one is kind of like all over the place, no relationship. So they don't always have to be linear, but a lot of times we'll deal with the linear ones. Okay, so it says two variables that are linearly, which are linear makes you can make the straight line, that are linearly related are positively associated, meaning the dots, the scatter dots, seem to be heading in an upward direction. When the value of one variable increases, the value of the other also increases. They're said to be negatively associated if when one increases, the other decreases. So if the dots seem to be going downward. So the linear coefficient, or the Pearson product moment correlation coefficient, I always just call it a correlation coefficient, is a measure of the strength and direction of the linear relationship between two quantitative variables. The Greek letter rho, which kind of looks like a P, is the population coefficient, correlation coefficient. So if you were able to do the correlation coefficient with and used data that was every single person in the population, we would call it rho. But most likely we're going to be using R because that's the sample correlation, because usually we don't have the whole population and we just do a sample from the population. So we use R to represent the correlation coefficient. Now there's an ugly formula to calculate it. We're not actually going to use this formula because we can calculate it on the calculators or using StatCrunch. But with this formula, we have, to get the R, we have the summation. The summation means you're adding things together. So you're calculating out this stuff together and adding. So this x1 would be, like if I had some sort of data, the x1 would be a specific point minus x bar, and x bar is the sample mean, divided by s of x. S is the sample standard deviation. So what you're doing is you're taking your x value from your data, minusing the mean of the x's, and dividing it by the x's standard deviation, and then you're timesing that by the y values data minusing the y's mean divided by the y's standard deviation. And then when you times those together, then you'd go plus, and then you'd take another data point and then do the x value minus the mean over the standard deviation times the y value minus the mean over the standard deviation. And you would keep doing that for every single one of these dots. And then you divide that by n minus 1. Now again, we're not actually going to do that because I can do that in StatCrunch. Okay, so I found a problem from your 4.1 assignment, and part of it says find the linear coefficient. So to find that correlation coefficient, you take your data and then open in StatCrunch. And then if I go to Stat, Summary Stat, instead of doing columns, I come down here where it says correlation. And then if I wanted to find the correlation of the lengths or the weights, you just find the one that you want. So I don't know what this one asked for over here. Determine the correlation between the weights and the lengths. Okay, so yeah, so I want to select both of them. And then I can come down here and hit compute. So it tells me my correlation 0.711, and that's what this said the answer should be. This first part on this problem, where it wanted you to select the graph, notice they all had length, 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 and then weight going up, except for this one, the odd one out. I can get StatCrunch to graph things for me by going graph, and then if I graph, that's a scatter plot. My x variable, I would go with length. My y variable, I would go with weight. And then I can just go ahead and compute. And then I get this. Now notice my scale here is a little bit different than what they have here, but I should get a good idea comparing those. When you look at the numbers, it looks like this right here is matching most closely with this one right here. Okay, so when it asks for that correlation coefficient, make sure to do it in StatCrunch. Okay, now properties of that correlation coefficient. Your answer should always come out between -1 and +1. The -1, if you get a negative number out, that just meant it has a negative linear correlation. If the number comes out as positive, then it's a positive correlation, meaning the -1, the dots would have been going down, the scatter plot would have been going downward from left to right, and a positive number would have meant the dots were like heading upward from left to right. If r equals 1, then it's a perfect linear relationship, meaning that line of best fit, that linear line, all of the numbers on your scatter plot would have landed directly on that line exactly. And then if your r was -1, then that line of best fit, every single point from that data set would have landed on it, so it's perfect. So usually it's not perfect. So usually, but if you get a number near 1 or near -1, then the closer it is to 1 or -1, then the more tightly the scatter plot points are around that line of best fit. Okay, so it says the closer r is to +1, the stronger evidence of a positive association. The closer it is to -1, the stronger the evidence to a negative association. If r is close to 0, then there's little or no evidence exists of a linear relationship between the two. Now, r close to 0 doesn't imply no relationship, it's just not linear. So if the scatter plot looked like it could be one of like these parabola type shapes, then our relationship would be close to 0 because that's not linear. So this one's an example of the correlation being +1, a perfect relationship. This one would be a strong relationship. It says that it's 0.9. This one, it still looks like it's a positive correlation, but the dots are not as tight. That one says it's 0.4. And then a perfect negative, a strong negative, a moderate negative, and then this would be no relationship, no linear relationship. And it also has a correlation close to 0. Okay, so this is what I had already just showed in StatCrunch. So remember to get your R. So from this data set, the R was 0.773. So again, we hit stat, and then summary stat, correlation, and then you select both your variables, and then you can compute your correlation. Okay, so now once you have that correlation coefficient, we need to test to see like if it's good to use for a linear relationship. So it says step 1, determine the absolute value of the correlation coefficient, because the correlation coefficient could come out as a negative or a positive. So when we're testing it, we don't care if it was negative or positive. So we just do the absolute value. And then it says find the critical value in table 2. So if you pull out your reference sheet that I gave you guys at the start of the beginning of the quarter, that you're allowed to use for every test, if you flip several pages in there, there'll be one that says table 2, which is kind of nice because then you don't have to like open up extra tabs in StatCrunch. But we do have, StatCrunch usually has a tab that you can click to see this table in each question. So like this one right here, it had the click to view the data, and then it says click to view the critical value table. So I can click there and it gives me the critical value table. So again, the same information is in your reference sheet that you're allowed for the test. It's kind of nice to have it in the reference sheet so you don't have to have this up while trying to look over here on the question. But anyways, what this is saying is you find the critical value in the table for the given sample size. So for this problem right here, when we were doing the drilling, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers in that. So then looking at this table, my sample size is 12. So I just come to here. Oops, I can't write on that. Okay. And it says 0.576. So if my correlation coefficient is greater than the number I see from the table, and on this one it was 0.773, 0.773 is greater than the 0.576, then that means that there is a linear association for this data. So then that's what step 3 says. If the absolute value of the correlation coefficient is greater than the critical value we saw from the table, we say the linear relationship exists between the two variables. If the value from the table is bigger than your correlation coefficient, then we say there is no linear relationship. So there still might be a relationship because it could have something like this graph here. There could still be a relationship, but it's just not linear. Or it could just have no relationship at all. So then this one says the correlation between the drilling depth and the time to drill is 0.773. The critical value when n was 12 was the 0.576. Since 0.773 is greater than 0.576, there's a positive linear relationship between the time to drill 5 feet and the depth at which the drilling begins. Okay, so this one says, according to the data obtained from the Statistical Abstract of the United States, the correlation between the percentages of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.94. So what that means is it's saying if you did a graph and graphed women with a bachelor's degree and unwed mothers, they're saying that it had a 0.94 relationship. So that's pretty close to 1, which meant if you had like the scatter plot, it's pretty linear. So it says, does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unwed mothers? So if you have more women with a bachelor's degree, does that mean that that's causing more women to be unwed mothers? Okay, and that wouldn't even make sense. So even though you can get the data that deals with how many women have a bachelor's degree and how many women are unwed mothers, and you can graph them together, it doesn't mean that these are related to each other. There can be something else that's affecting that. So here it says, Certainly not. The correlation exists only because both percentages have been increasing since 1990. It is this relation that causes the high correlation. In general, time series data, or data that's collected over time, may have a high correlation because each variable is moving in a specific direction over time, both going up or down over time. One increasing or one can be increasing while the other is decreasing. When data are observational, we cannot claim a causal relationship exists between the two variables. We can only claim causality when the data are collected through designed experiments. So apparently from 1990, the number of women getting bachelor's degree, the percent of women getting bachelor's degree has been increasing. So has also the number of unwed mothers, but these two aren't affecting each other. It's just because over time the bachelor's degree is increasing and the unwed mothers is, but it's not one causing the other. So another way to look at two variables can be the way variables can be related even though there's not a causal relation is through lurking variables. A lurking variable is related to both the explanatory, the x-axis one, and the response variable, the y-axis. So there's some other variable that relates to both of them that might make it look like the explanatory and the response are related to each other. For example, ice cream sales and crime rates have a very high correlation. Does that mean that local governments should shut down all ice cream shops? No, the lurking variable is temperature. As air temperature increases, ice cream sales increase. So they sell more ice cream in the summer than they do in the wintertime. That would make sense. And then apparently crime rates also increase when it's warm outside. So um, crime rates increasing because of the temperature, ice cream sales increasing because of the temperature, but it's not ice cream sales that are causing the increased crime. And then one more example, this one deals with bone mineral density study and lurking variables. So it says this figure shows the scatter diagram of the data, the correlation between the number of colas per week, so how many Coca-Colas you drink per week, and the bone mineral density is negative 0.86. So looking at this, it looks like it's a negative correlation. So it's saying like the more colas you drink, the less your bone marrow density, if colas were um, having that effect on the bone marrow density. So it says the critical value for the correlation with n equals 5. So that critical value again was from the table, or let's see, n was 15. So if you had the little chart, 15, it says it's 0.514. That's where this came from. Because that correlation coefficient, the negative 0.8, the absolute value of that is positive 0.8, which is greater than 0.5. We conclude a linear negative relationship exists between these. Can the author conclude that increase in number of colas consumed causes the decrease in bone mineral density? Okay, so even though there's this relationship, we can't necessarily say that drinking more colas is causing the bone marrow density to go down. They could say there's a relationship between them, but not necessarily that the drinking Coca-Cola is causing it to go down. So it says some examples of lurking variables could be body mass index of the people, how tall people are, whether they smoke, their alcohol consumption, their calcium intake, their physical activities. So all of these things could be coming into play about that bone marrow density. So it says the authors were careful to say that increased Coca-Cola consumption is associated with lower bone mineral density because of potentially lurking variables. They never stated that increased Coca-Cola consumption caused the low bone marrow density.